Okay, so in this one, the vector field F has components x, y, and z. S is part of the plane x plus y plus z equals 2, and it's the part that lies in the first octant and has upward orientation. At some point, you're going to want to graph that surface, so let me graph it right now. So this is one of those, and I've shown you how to graph these. If you just, in the first octant, if you just graph what? Plot the intercepts, connect the dots, you're going to get a nice triangular piece of the plane, right? So what are all the intercepts? The non-zero coordinates are all 2. So that's what we'll plot. So we'll go out 2 on each axis. And I'm just going with the usual orientation, x, y, and then z. Okay, so there's the z-intercept, the x-intercept, the y-intercept. Connect, if you, I just barely missed it, darn. Connect, connect. And then really, S is this surface here. Okay? So, we're going to use, for flux, the generic formula. I always write it down. If you just write it down every time you use it, you'll remember it. It's the integral over S F dot n ds. Generically, that just means the flux integral, right? And then what's the calculation formula?
Plus or minus del G.
So once you change to the calculation formula, it's actually, you're going to project that surface down in the xy plane. So we'll call it an integral, double integral over R. And then it's going to be plus or minus del G. Which one is it going to be in this case? Since it's an upward orientation, so you can picture the normal vector with positive k component like that, right? So it'll be just del G, because by default, I take that one to have positive k component. And then dA. So what is uppercase G? It's almost right in front of us, right? We make sure that the z coefficient is positive and get everything on the same side with the z coefficient positive. So it's good enough as it is, but technically, I suppose you'd have to set it equal to 0 like that. So that this is G, uppercase G, right? If you solve for z in terms of x and y, then that's lowercase g, if you're trying to remember what's what. So what's del G then? Gradient of G, what is that?
I plus J plus K.
Yeah, it really is. It's I. I'll use this notation here. I, so 1, 1, 1. Would you buy that?
And you just took the partials of F.
Partials of it, yeah. That's the gradient, yeah. So it's del G. It's equal to the partial of G with respect to X. Just out of habit, I called it F. And then partial of G with respect to Y is your J component. And then partial of G with respect to Z is your K component, right? But I wrote it in component form. Everybody with me? Okay, so that's del G. And then what does the formula tell us to do with del G? Dot it with F. Now, ultimately, it's a double integral, so if you have 3 variables, you're going to have to do something about it, but I wouldn't worry about it yet. So just write down F right next to it. I mean, you don't have to do this part. It's easy enough to look at both at the same time, but it's nice to have them next to each other. And then you take the dot product of those two things, don't you? So what does F dotted with del G turn out to be?
X plus Y plus Z.
Yeah, not too bad. But that's not the integrand we're going to go with, is it? Because we're turning this surface integral into a double integral, and you have to have only 2 inputs there. And usually it's x and y if you integrate in the usual way. And so what do? So if we solve for z right there, kind of hard to see. If we solve for z right there, what do we get? Z equals, there you go. And so if we plug in right here, 2 minus x minus y, what do we get? 2. Yeah, that's not so bad, right? You've seen worse integrands than that. Okay, yeah, we can handle that one. Okay, let me back off the view here. Okay, so set up the integral for me. Oh, wow, what do we kind of need? We don't kind of need. We need, well, what R, the region of integration R, right? So in my 3D picture, that's this guy, right? Imagine that plane being projected down, the plane in space being projected down into the XY plane, and that region in purple's R. And if you want partial credit, say you get the wrong answer, it's really easy to get a wrong answer on these problems because there's so many steps. But if you show me a picture of R and you're going in the right direction, you just make a silly mistake, you're going to get a lot of partial credit, right? Whereas if you make a mistake and you don't show me a picture of R, you're not going to get as much partial credit. So show a picture of R, long story short. And if you do that, well, we can figure out the equation of the line pretty quickly, can't we? So we know the x-intercepts are 2. So a couple ways to do it. You could just go ahead and find the equation of that line, or you could just set z equal to 0, right? In the given equation for the surface. Oh, what do you get? Solve it for y. You get y equals 2 minus x, which is, of course, what you get if you use like y equals mx plus b to get the standard or the slope-intercept form of the equation of the line. Okay, so everybody sees what R is. Let's use the standard vertical rectangle setup, which corresponds to what order of differential? dy dx. Okay, I think we're ready. So I'm just going to say this: flux is equal to the double integral over R. Okay, what are the limits of integration then? Inner limits 0, bottom to top of the representative rectangle, to 2 minus x. And then what does x run from? 0 to 2, 2, and then dy dx? Oh, okay, that's not the worst one in the homework, is it? All right, so we might as well evaluate it. Won't take very long. So bring the 2 on the outside. We still have the outer integral, and then we would get what if we integrate, disregarding the 2 since it's on the outside, we get y evaluated from 0 to 2 minus x, which is just 2 minus x. Does everybody see that? And then integrate that, what do we get? 2 times 2x minus 1fx squared, evaluated from 0 to 2. What does that wonderful whole thing become? So just 2, then we get 4 for this one when we put in the upper limit, right? And then minus 2. So 2 times 2 is 4.